Japan built a wall so massive most people on Earth have never heard of it. It is taller than a 4-story building. It runs 400 kilometers. It cost $12 billion. 400 kilometers, New York to Boston and back twice. Every inch of it built by hand. That was 2011. This is today. The wall exists because of what happened on the left. Wait, this wall is now so high you literally cannot see the ocean from your home.
My husband ran toward the sea. I never saw him again.
Every meter of this wall was paid for in grief. Now watch what they actually built. But engineers warned, if this wall fails, it could make the next tsunami far deadlier. March 11th, 2011. The ocean floor moved 50 meters in 3 minutes. What came next was unstoppable. That rupture displaced 500 cubic kilometers of ocean. The wave crossed Japan in 30 minutes. Not a wave, a moving wall of black water, 40 meters tall. Nothing in its way survived. 90% of Japan's seawalls failed in that single hour. Every engineer in Japan took notice. The world's largest breakwater, $1.6 billion, destroyed in seconds.
It did not break from the front. Water topped it, eroded the back face, foundation vanished.
That is the engineering problem. One mayor, one wall, 3,000 people alive. That village gave Japan its blueprint, build it taller. Now you might be thinking, how do you design a wall to stop an entire ocean? Here is the brutal truth. This wall was never designed to stop the 2011 scale wave. Here's the crazy part. Most of this wall is underground. Only 14 meters shows. Engineers modeled this wall 200 times in a computer before placing one single stone on the coast.
Wall height changes every kilometer. Taller on exposed headlands, lower in sheltered bays. Designed from wave data.
440 separate teams. If even one goes bankrupt mid-build, a gap opens in the wall. Zero tolerance. Before one stone is placed, survey ships drill the seabed. Every section is different below the surface.
3 foundation types: soft clay, dense sand, hard rock. Each requires completely different engineering underneath.
First task, demolish the walls that failed. Study every failure mode. Then build the new one bigger. 400 kilometers, measured meter by meter before a single machine starts digging. This step takes months. They cleared an entire coastal pine forest. Erosion matting follows the bulldozer within minutes. Always. The tide gave them 4 hours daily on the seabed. Every single minute was counted. The clay zones cannot even support a bulldozer. The ground is dangerously soft down there. Steel road plates spread the load. The machine floats above the mud. Simple, effective, crisis over. They are building the foundation 25 meters below sea level, in the active surf zone, right now. Divers guide 5-ton boulders into position underwater, in the same ocean that just destroyed the coast.
Engineers check the underwater progress by sonar. They cannot see it. They must trust the data completely.
Between boulders and fill sits a filter layer. Miss it, the wall slowly bleeds away. After weeks underwater, the rubble mound breaks the sea surface. Watch what comes next. That geotextile membrane stops fine soil particles migrating into the rubble. It works silently forever. An uncompacted mound settles unevenly. A settling foundation tilts the wall. Every roller pass is preventing failure.
A 1 to 1 in 5 slope angle exactly. Steeper and boulders slide. Flatter and waves will not break on it.
A platform is rising inside the ocean, from nothing. Now the real wall construction begins above. Sheet piles driven 10 meters into the ocean floor just to protect the wall toe. Z-profile interlocks. That connection transfers shear forces between every pile in the wall. Critical detail. That steel wall fights the retreating wave, not the arriving one. Backwash scour is what destroys foundations. One buried boulder deflects a 12-meter pile sideways. The entire alignment is now destroyed. Pre-drill the boulder first. Crush it. Then the pile drives straight through the cleared hole. Clean.
The wave going back out is more dangerous than arriving. Backwash vacuum pulls the foundation sand out.
30 dump trucks running 16-hour shifts non-stop. One breakdown stalls the whole compaction cycle. 300-millimeter lifts, no more, no less. Too thick and the compactor never reaches the bottom of it. Inside every seawall body, geotextile reinforcement layers, like rebar in concrete, but for compacted fill. 98% proctor density, or the inspector shuts the job down. Every single layer tested here.
Press your foot on 98% proctor fill, nothing moves. At 85%, sinks.
300 millimeters per day. 18 months until the first tsunami season with the wall standing. Counting. That clay core is the wall's internal waterproofing. Well-compacted clay stops water permeating through it. One night of heavy rain. 600 millimeters of slope slumped. The entire section is rebuilt from scratch. A drainage pipe network inside the embankment. Cover the slope with geotextile before every rain. Always. The wall hits 10 meters. Thousands of concrete panels are coming. This is the critical part.
This wall has sensors embedded inside it. Engineers watch it breathe and settle. Every day, forever.
The face must be perfectly flat before any panel goes on. One bump creates a stress concentration.
3 materials, 3 jobs. Grip the seabed, seal against water, carry the structural load. All one wall.
If one of these 7-ton panels cracks in the mold, it ruins the entire week's schedule. Every hairpin bar connects the panel to the crown wall. One missing bar breaks everything. Self-compacting concrete flows around every bar. Perfect face. No honeycombing. That surface must resist a tsunami. Wrong slump and the panel face honeycombs. One bad batch fails the whole production run today. Listen to that tap. Solid ring means good concrete. A hollow sound means this panel gets crushed. Zero tolerance for defects on tsunami walls. That panel is worth $800. It still gets crushed. 7-ton panels on narrow Japanese coastal roads. Flagmen at every junction. 400 kilometers to cover.
That bed is leveled to 5 millimeters. A hump cracks the corner of a 7-ton concrete panel.
That face takes a tsunami at 30 kilometers per hour. It must hold for 100 years. 400 millimeters lap sounds boring, until you picture a tsunami ripping each panel off the wall. That rubber water stop swells when wet. The bigger the wave, the tighter every joint seals itself. Straight panels on a curved coast. 20-millimeter gaps opening. Water forces through and undermines everything below. 37 unique panel shapes. CNC machined molds. Every gap closes to zero. One curved bay, perfectly sealed. 1 week seals 400 meters, but the 2022 deadline is counting down. 440 teams racing simultaneously. The crown wall nose throws overtopping water back over the seaward side. One detail protects thousands. The crown wall grabs every panel below through hairpin bars. One integrated structure, not individual stacked pieces. Pump boom maxed at 15 meters. If it fails mid-pour, a cold joint forms. wall compromised.
10 degrees from vertical. That single angle throws overtopping water outward instead of crashing inward. Simple genius.
The only decoration on 400 kilometers of wall, a stamped wave pattern on the coping. They measure the crown wall height for 5 years after completion. Monitoring never stops.
6 materials. 6 engineering functions. From outside, it just looks gray. It is not.
The back matters as much as the front. Back face failure is what killed the old ones. If water tops the wall, it must go somewhere safe. The landward drain is that escape route. 32-ton concrete blocks. Each one must interlock, or the entire armor layer shifts in the first storm. One leg always points upward, catching the next tetrapod above. That interlock absorbs wave energy on impact. They are not placed precisely, they are dropped. They find their own stable position, chaos creating order. The gaps between tetrapods are not a weakness, they are the mechanism. Water flows through, energy dissipates.
1 liter of water completely absorbed. Now imagine that multiplied by 50 million tons of tsunami.
There is a formula for this, Van der Meer equation. Input wave energy, output minimum armor weight. 40 tetrapods per day, 400 kilometers of coastline to armor. This yard never stops, day or night. Below the waterline, tetrapods pile up unseen. Sonar shows what no diver can reach at that depth. 3 lines before the wall, rubble mound, sheet pile toe, tetrapod armor. The tsunami exhausts itself first. Every wall section is tested in a wave tank right now, and some results are unexpected. 443 gaps in the wall, each one a death trap if a single floodgate fails to close. Floodgate concrete is twice as thick as normal. This is exactly where tsunami forces concentrate hardest. 70 seconds from alarm to sealed, the only window before the wave hits the coast.
A seismic sensor triggers automatic closure. No human needed. Earthquake starts, gate begins closing immediately.
15 millimeters clearance, 50 tons of steel, 40 kilometers per hour coastal wind during installation. 1.5 times design pressure. If one of 14 seals leaks, the gate completely fails. 40 liters per minute through a 2 millimeter gap. Under real tsunami pressure, that gap becomes 20 millimeters. 2 millimeters ground off. Retest. 0 leaks. 3 hours of machining saves a whole town. A driver caught in this gap when the alarm triggers, the gate closes in 70 seconds. A 22-meter steel curtain must seal the river mouth before the tsunami wave arrives at the coast. Stored open at the top. Gravity closes it. Power fails, the gate still comes down. 443 gates, 1 command room, 4 minutes 20 seconds. Japan drills this every March 11th.
400 kilometers of wall. 1 screen. Every gate, every sensor, every alarm. The wall thinks for itself.
On cliff sections there is no beach. The wall goes directly into the rock face. Rock bolts. 2 meters into basalt. 50 kilometers per hour coastal winds during drilling. Wall bolted to mountain. Concrete sprayed at 100 kilometers per hour bonds to rock better than poured. The cliff becomes the wall. The tsunami hits concrete bonded to shotcrete bonded to basalt. 3 materials. 1 integrated face. Nothing moves. A submerged breakwater trips the wave 200 meters offshore before it even reaches the main coast wall. A 60,000-ton box floating in 3-meter swells, being sunk to 63 meters. Watch what happens. The tug loses steerage in 30-knot winds. That 60,000-ton box drifts 8 meters off its mark. The rebuilt Kamaishi breakwater is stronger than the world record it replaced. Always build back stronger. If this panel fails the strength test, the entire week's batch goes to the crusher. 2 millimeters of carbonation. The reinforcement inside will not see sea air for at least 100 years. The independent inspector can fail any section and order demolition. 440 contractors under that pressure constantly. Twice the design load on the gate frame. Engineers watch strain gauges. It holds well. 14 millimeters of differential settlement across 400 kilometers in 2 years, on coastal sandy ground. Exceptional. A 7.4 earthquake strikes. The sensors fire. All 443 gates are now closing simultaneously.
0 cracks, 0 shifted tetrapods, after a real 7.4 earthquake. That result is extraordinary engineering performance.
Watch this. The pump is running on the last section. 400 kilometers is almost sealed, almost alive. A helicopter is flying the full 400 kilometers right now. What it photographs will change engineering forever. These staircases are not scenic overlooks. They are emergency evacuation routes designed from crowd flow science. People cycle along the top now, walk dogs, run every morning. The wall became a daily promenade.